So this is the second lecture about the general relativity and about the metric tensor generally. In the first video, I have discussed about the Christoffel symbol and the derivation of the geodesic equation. In this particular video, we are going to do the metric tensor, and you will say which manifolds metric tensor. So we are going to derive it for the flat space. Yes, first of all, flat space, because we have to build intuitions about the metric tensor first. After you will build intuition, you can go for some advanced metrics like Kerr metric and Schwarzschild metric. But first of all, you have to build intuitions about what is metric tensor, Christoffel symbol, what is the meaning of calculating Christoffel symbol, what is the general meaning of metric tensor, and we will apply this all on the flat space and we'll see what exactly it is. And then if we'll discuss all this, you can generally move to some advanced metric. But first of all, to build intuition, this is lecture number 2 on the metric tensor deriving with the flat space. So actually there are two methods. First method we are going to use here is using the differential, which is ds square is equals to metric tensor dxi and dxj. So this, what is this? So this is nothing, it's just the measuring of the distances between the 2 points on any manifold, and what you will see that on flat space this particular equation reduces to our general Pythagoras theorem. Yes, you heard right, general Pythagoras theorem. And what is it? So it's nothing, it's ds square is equals to dx square plus dy square when our manifold is flat. Okay, and this is very important. And the second method is second method is using this principle that the metric tensor is nothing, is just the dot product between the basis vectors I and basis vectors j, and this is what this particular indices of this metric tensor says. It means the basis vector multiplication dot product between I and j basis vector. And why this is important? Because this is very important to know what exactly is the notion of this metric tensor. You will see after doing the dot product, you will get something about the angles and measurements, and that what this particular metric tensor do. It tells about the, also you can set it in this equation, it can tell about the distances between, or the lengths, you can say that. In this particular, it can tell about the angles between the vectors on the curved space, and that's why this metric tensor is very, very important. And it's very basic, in fact it's fundamental. You will see I have said that how this particular first equation converts into the Pythagoras theorem. And yes, there is a metric for the flat space which we are going to do here and derive it. So let's start, and the method that I'm going to choose is this first method, because second method is quite lengthy, because first of all you have to find out the basis vector, and after finding out the basis vector you have to do all of the matrix multiplications and all that stuff. That's why this is quite good. Okay, so I will choose this first method. So let's start. First, so generally in the flat Euclidean space in 3 dimension, the distance is ds square is equals to dx square plus dy square plus dz square. Okay, but what I'm going to do is that I'm going to do all calculations in the polar coordinates. Why? Because when you will do polar coordinates, then you will only realize the importance of the metric tensor, the Christoffel symbol and all that stuff. Because the Christoffel symbol is 0 in the Cartesian. Yes, the Christoffel symbol is 0 in the Cartesian coordinate system, but it is not 0. Some of the components are not 0 in the polar coordinates, and that's why it's important. That's why I'm going to convert in polar coordinate. You also know the formula, that is for x is equals to r 1 minute. Okay, so x is equals to r sine theta cos phi, y is equals to r sine theta sine phi, and z is equals to r cos theta. So these are the 3 formulas that you can substitute by taking the differential. I'm not going all calculation because it will increase the time. So that's why the final calculation here I'm showing in the polar coordinates, which is ds square is equals to the You have to do this, okay? I'm not doing the call, it will increase the time of this particular video, that's why. So dr square plus r square d theta square, so this is theta, okay, plus r square sine square theta and d phi square. Yes. You can see that here I have derived the differential. But what now? So if you have watched my first video about the metric tensor, I have said that the distances between the 2 points can be used by using that particular equation. You will say how? So if you know how we are going to check. So dgij, let's say, is the metric tensor. 1 minute. Okay, so it is equal to, there are some components. I'm going to write out the components in the form of polar coordinates. First is g theta and theta, second is g theta r, and third is g theta phi, and second is, 1 minute, second is g r theta, g rr, g r phi. Let me extend this. Third is g phi theta, g phi r, g phi phi. You will say how I have written this. How I have written this? Because you know our Cartesian system is not there. There is a polar system. There is theta, r and phi, and it is equivalent to writing this. Maybe you will find intuition how I have written this. Just like this, suppose that there are 1, 2 and 3 indices. Just like here is theta, r and phi. Theta is 1, 2 is r and 3 is phi. So let me relate this. G11, G12, G13, 1 minute, okay. Just like the G21, G22, G23, and just like here, let me erase this, G31, G32, G33. Now you can compare this. G11 means theta theta, yes, you can see that here is theta theta, and G12 means theta r, and you can say that it is theta r, and G13 means theta and phi is in theta and phi, okay. Now G21, so G21 means r theta, as you can see that here is r theta. Second is G22, which means rr, you can say that it is rr. Third is G23, it means r phi, you can say it is r phi, okay. So you can build the intuition, you can see that how I have compared this, and using the numbers you can generally see that yes, this is correct. You will not be confused after seeing this matrix, because you will say that yes, these two are same. Okay, so you will say why I have written this. So if you know the basic definition that I have now written, that g theta theta means theta cap, 1 minute, g theta theta means e cap theta basis vector, sorry, this is phi sine, let me, okay, basis vector and this way. So both are the same basis vectors, and we are doing the dot product, and you will see that angle between them will be 1 in the general form, the flat Euclidean space. So this means this is equals to 1. But if we will multiply some basis vectors, like let's say e theta, 1 minute, e theta with er, you will know that these both are orthonormal, and if they are orthonormal, the value is 0. It means besides, let me write, 1 minute, let me write this here, that besides g theta theta, g rr and g phi phi, this is not theta, okay, this is phi. Let me write this clearly because you will get confused. G phi phi, besides all of these particular components, beside this, all of this particular components, this diagonals of component are 0, only the diagonal components are non-zero, all of these are 0. Because how? Because you will see that this g means phi and theta and they are orthonormal, they'll become 0. These are basic vectors, okay? So it means our notation reduces to this: g theta theta 0 0 0, g r r 0 0 0, and g, 1 minute, and g phi phi. For the flat space, remember this is only for the flat space. There is not a very universal truth that always it is 0. For the different types of our curved space, maybe the all components are 0, all components are non-zero, whatever can be. So it is only for the flat space. Always remember this is only for the flat space. Then you will say, why I have written this? So I am trying to connect the two things. Which two things? So I have written, I have derived that ds square is equals to r square plus r square d theta square, theta it is, okay, plus r square sine square theta d phi. Let me write it clearly: sine square theta d phi. What I'm going to do is that I'm trying to build the intuition, and you will say how? Because if you have seen my first video, we can represent the differential, we can represent the distances between the 2 points as g, any of these indices. Like suppose that g11 I am taking arbitrary, okay? So g11 r square plus g, I'm taking arbitrary, so please don't connect this. Let me choose. So ds square can be written as, suppose that gij x dot x plus gki y dot y, and this is how there is a relation between the metric tensor and the distance between the 2 points. It means besides every of this particular square, there is a metric tensor here. There is a metric tensor here. The coefficients, you can say that of x square and y square, there is a metric tensor. Just like this, you can relate that besides r square, what is here the coefficient? 1. Yes. And here, what is the coefficient of d theta square? R square. And what is the coefficient of d phi square? Sorry, here square. So r square sine square theta. It means these are our metric tensor. Sorry, components of metric tensor. Okay, so let me take another example. 1 minute. Suppose that we have a differential ds square, and I have written a formula jij is equals to dxi dxj, okay? Suppose this I have chosen value of I and j is running from 1 to 10, let's say, example. So the distances between the 2 points is equals to g, first of all 1 1 dx1 dx2, okay, plus g 2 2. Suppose that I have taken example g 2 2 dx2 dx2. Similarly g 3 3 dx3 dx3. So what you will see here is that besides every this notation dx and matlab, you can say that the norm of these particular dx and differential, there is a metric tensor here. There is a metric tensor here. And you will see this is similar to our this particular situation of the differential we have derived in the polar coordinates in the flat space, that here d phi square has a coefficient of r square sine square theta, d theta square has a coefficient r square, and r square has a coefficient of 1. It means our 3 non-zero metric tensors here are these values. Yes, this is the thing. It means g I j is equals to 1 0 0 0 r square 0 0 0 r square sine square, 1 minute, r square sine square theta. Yes, this is the thing. These are our non-zero diagonal coefficients of our metric tensor. 1 r square and r square sine square theta, and these are nothing, these are just the coefficients, as you can see that here. These are the coefficients of the d theta square, d phi square and the r square. And we have finally derived it using the comparison, using the basic line element thing. That's why I have written this method as a line element term. So this is our video on the derivation of the metric tensor in the polar coordinates for the flat space. Okay, second method is also quite useful, but second method is quite lengthy. That's why this method I liked, that's why I use this particular method. The fact is that this method is given in the David Tong's notes. Okay, David Tong note. You can find this derivation. Okay, the fact is that in David Tong note you will see that he had done all the things directly. Okay, but I here explained all of that stuff because David Tong assumed that you all know about all that stuff about the how to do the norm and how to write a covariant derivative, all that stuff. That's why he had only assigning all of that particular terms and directly written all this. He has directly written all this. Okay, but I here explained all about the fact that how to write the differentials and all of that stuff. So maybe in the second video we will discuss about calculating the Christoffel symbols. Okay, this is another very important thing for calculating the Christoffel symbol. So let me write the symbol. I like the symbol very not. I 1 minute. I mu nu symbol I like. So maybe we'll discuss about calculating the Christoffel symbol and some basic principles about the Christoffel symbol in the next video. So this is my first video on deriving the metric tensor for the flat space time. So thank you for watching.